Hello, this is a video for COMP345. This is week 12, slide set 11. I'm going to make only one video for this slide set. It's going to be a rather long video, but I prefer at this point to make only one video rather than two. So please bear with me for the length of this video. So here we go. Okay, sorry about that. So this is about templates. So one of the things I want to clarify, as you will see later on in this video, is that this particularity of what is C++ templates versus what you learned earlier on, which is Java generics. Again, as for many things between C++ and Java, you may look at C++ templates, the syntax that you use, it may make you think that this is the same thing as Java generics. However, it is actually very different. It looks like the same, but it's behind the scenes different. And it has also, in the case of templates, it has the way it's actually processed. If you don't understand how it's processed, it's going to be very confusing for you. Essentially, what happens when you use the C++ templates is that there's a template instance generator that is going to generate some code, and then that's this code that you are compiling. And for example, that's why if you have errors in this code, then this is going to be errors on generated code, which is notoriously leading to cryptic error messages. So that's one of the things that people see when they first tackle with templates, that it's hard to understand what's happening when it actually does not work. So if you understand how it works, it helps you understand these cryptic messages. So as I like to do in the beginning of topics, let's do some kind of history or higher level description of what this is we're talking about here. So essentially in C++, that generic programming is done using template metaprogramming. So let's even backtrack a little bit and explain what is metaprogramming. So anytime in general you see meta in front of a concept, that means this concept is kind of reflecting upon itself. So here, if you talk about meta programming, in a way, what you're talking about is either you are you're writing programs who are generating other programs, or you're talking about a program that is able to reflect upon itself, reflect upon its own execution. Okay, that's why, for example, in Java, you have Java reflection that allows a Java program to be aware of its own definition. Okay, so that's what is meta programming. It's about writing programs that can either generate programs or reflect upon existing programs, including themselves. Okay. So then that brings the notion, very often you would have the language for metaprogramming is not necessarily, the language that you use for metaprogramming is not necessarily the same as the language of the programming language itself. For example, if you're using a language to generate programs, this language that you use to express the generation of programs is not necessarily the same language as the language for which you generate the programs into. Okay, so you might have a difference between the meta language and the language that you reflect upon, which is the object language. Okay. We will see later that in C++, in fact, the C++ language, you might say, is a hybrid language between the meta language and the object language, which is C++. So in other cases, in more restricted cases, for example, like with Java reflection, then it's basically some kind of library that is added in the Java language that enables a Java, for example, class or object to be able to reflect upon itself. Example that enables you, when you use Java reflection to, for example, ask an object, what are the members of your class? Or even to tell an object to add some members to their class or remove some members to their class, things like this. Okay. Not everything is possible, but it reflection allows you to have objects that can reflect upon their own definitions. Now, you might say this is a very advanced concept, so that must be something new. In fact, it is not at all new, as for many things in computer science that we think are new nowadays. They have their history dates back to the beginning of the history of computer science. Same thing as for metaprogramming. So in the language Lisp, which was one of the first languages invented in the 1960s, or evolved, I might say, languages invented in the 1960s, you had this notion of a function that was available for a program, which was the eval function. You would see basically that's a function that was available through the runtime system that allowed you to basically pass a string to eval, which would then basically compile this string into a program, which then the program that receives the result of eval can actually add this compiled program to its current execution. That would allow you, for example, one of the things it might allow you is to actually have a program actually change its own behavior at runtime. That's a very, you might say, revolutionary concept, but it actually appeared really early in the development of programming languages. That's also something that is, of course, dangerous to have a program that can actually change its own definition. Okay. That may lead to very interesting things, but also very problematic things. So, and also another flavor of this is there was a tendency in the 1970s and 80s to have, to prove that a language was really useful. One of the things you could do is to actually implement the compiler and the runtime system of this language that you use to execute and compile these programs in the language itself. So if arguably, if you can use a language to develop a runtime system and compiler, then that's a very good language. Plus, it also allows potentially you to have the runtime system be able to manipulate programs as objects, okay, which is kind of the ultimate form of metaprogramming and reflection. Okay. One of the notable languages that were achieving that is the Smalltalk, the implementation of the Smalltalk language. Smalltalk was revolutionary in many, many different aspects. It was one of the, for example, one of the first industrial, you might say, implementation of object-oriented programming languages. Nowadays, you have many different languages that have capacities like this. There is a great correlation between what is called dynamic languages and languages that have metaprogramming and especially reflection. So let's go now to what is template metaprogramming. So the idea here is that what you do is to write a template for example, a class, for a function. This template is written in some kind of meta language. And then this meta program essentially is, its goal is to actually generate components. So if you have a template class, if you have you pass this template class to a template processor, so it receives the template class definition, and then depending on what you ask of it, then would generate classes, for example, in C++. So that's exactly what happens when you when you compile your templates in C++. The template declarations or definitions that you have are template declarations. They're not C++ programs. And then the template processor actually receives them and generates C++ classes, regular C++ classes. So that's what the main difference between C++ and Java, C++ templates and Java generics. Java generics are not about metaprogramming. A generic class in Java is a class as any other class that is executed at runtime. The class that you write in your program is actually executed at runtime. Whereas a template in C++ is not something that executes at runtime. It's the, for example, class that is generated by the template generator, the template processor that is executed at runtime. It's the result of the processing of the template by the processor that is executed at runtime. So here in this case, you need to have a meta language. In C++, you actually have a hybrid language. So the language that you use to actually express your templates is actually using the C++ language inside of the definitions of the templates. So that's why it's kind of hard to see the difference between the two. Okay. I'll point out these differences as we go with some examples. So first, you declare the template using the meta language, and then so for example, you would have a template class that is defined and declared. And then eventually in your code, you would eventually use this class. For example, you could have all the very good example of templates is the Stl containers, which are all templates. So let's say you have your vector. So you would have your vector, the definition or the declaration of the vector template, which is in one of the libraries that you are using in the Stl libraries. And then in your code, you're actually declaring, let's say, a vector of int. So as you're declaring this vector of int here, and when you compile it, it would actually compile, call the template processor to actually generate a class vector of int out of the template declaration for vector. So that now you have in your code a class vector of int that you can actually use. If later on you use a vector of char, then it would then ask the template processor to generate a class vector of char, which you would then use. So you see that you have the generic definition, the template declaration, which is used to actually generate for each of the different uses of the template. The compiler will call the template processor to generate a specific class for each specific different uses. That's what I mean here, but when you refer to this template, when you use this template, this class template in your code, then it would actually have the template processor to generate a class, a regular class. Okay. The classes that are generated by the template processor are regular classes as any other class that we saw before, as we saw before. And then, of course, there's some tweaking to be made as you're actually using these objects in the code after the declaration. Then you have these references to the classes themselves have to be, when you use, for example, the members of this class, then it has to refer to the class by name, the class that was actually generated by the template processor. And that's why, as you compile this code, it's possible that if you refer to some member of this class, then it's gonna, for example, the linker might refer to a class that you don't know about, a class that is not in your code. It's actually a class that was generated by the template processor that is now compiled and linked with your program. So this is code that is not part of your program. And of course, this can lead to very cryptic as well as confusing errors. Okay. Then, okay, so as I said, in C++, what you have is actually a hybrid language. So when you declare a template, it starts with this header template in angle brackets, signifying this is a template declaration. So this part is actually a part of the meta language. But then inside of the template, you're allowed to use C++ constructs, for example, a class. Okay. So it is the template, the meta programming language for to use to express the templates is actually a hybrid between this template language and the C++ language. Okay. So what's the goal behind templates? And simply stated, what's happening here is that what you want to do is you may have a certain design idea in mind, and then you realize that this design can actually be applied to different types. Best example is, of course, the Stl containers. So if you have, for example, a stack class, so a stack of int or a stack of characters or a stack of double or a stack of anything always has the same behavior. If you go pop, basically is taking the first element and then removing it and then returning it. This behavior is independent of the type of elements that you have in your stack. So that's always the same idea when you have a template, is that you have a certain behavior that is actually applicable to a lot of different types. So you want to make abstraction of the type of elements that is manipulated by the mechanism and allow yourself to express a common mechanism that applies across different types. Okay, so that's the main use of templates. You can do other things, but that's always an abstraction mechanism. Okay. That's basically it. Okay. So here's the compilation process. So that's what is different between your Java generics and your C++ templates. That's among other things. So I would say this is the most important difference. If you don't understand that, it's very hard for you to understand what's the difference between the two. So you might be at ease with designing programs in Java with Java generics, and then you go with C++ templates, and then you're faced with a lot of intricacies and very cryptic errors and so on. It may be hard for you to understand. If you don't understand this here, you'll be confused. That's the reason for your confusion, because you don't understand how it is processed. As for many things, as you saw in this course repeatedly, C++ is such that if you don't understand how it works, it's hard to actually use it. That's a very good example of that. Okay, so let's say, simple example here. So let's say I have a source file, or I have two source files. So these are two compilation units, right, as we saw earlier. So these are two CPP files. Okay. One of these CPP files is actually using a template. So for example, this file here is using, I don't know, a vector template from STL. Okay. So it is, for example, somewhere declaring a certain vector and then calling some functions that belong to this template vector class, or vector template class, or class template, sorry. So what's happening here is that as this code here is actually referring to a template, then the meta processor is going to be called inside of the compilation process when the compiler sees the use or referring to a template of any kind. Then it tries to find the template declaration for this template, and then would actually generate a class that corresponds to this particular use of template. For example, if in this source file here, you use a vector of int, then the template meta processor is going to find the template for vector, and then it's going to generate a class, a regular C++ class that corresponds to vector of int. This is going to be only for vector of int. If somewhere else in the code you use vector of strings, then it's going to generate another class, vector of strings. Okay. Then it's basically, and that's the sources I'm referring to here. So if this refers to vector of int and vector of string, then this is going to be a new class that the processor has generated, vector of int and vector of strings. As well as when you actually refer to these vector of int and vector of strings, then the code that you use to actually refer to these here will have to be somehow altered so that it actually refers, for example, if you're calling the methods of your vector class here, then it's going to have to either refer to this here or to this here, depending on if you refer to, of course, a vector of int or a string. So the source also has where you actually use these templates, these classes, vector of int or vector of string. It will have to somehow be adapted also by the template metaprocessor. So the template metaprocessor not only generates the classes, but also fixes the code that uses these classes to actually make them use the classes rather than the abstract template. Okay, so that's what happens for the compilation of this compilation unit. Now you see that this other compilation unit here in my graph here does not use any templates. So what's going to happen is that this one is going to be unchanged by this process here. If a source file does not contain the reference to any template, then the template metaprocessor is not involved in the compilation process. Okay. So if you are generating, you're compiling a program that never uses templates, absolutely never is the template metaprocessor involved in the compilation process. Okay, so and then what you have is this source file here that has been altered, this source file here that has been altered, and these two files or classes that have been generated that are part of this compilation unit here. Then this is actually here regular C++ code that then is fed to the regular compiler, which will compile that and then basically put all the pieces together, and it's linked to get together, and then you have an executable. Okay. So you see that if you're compiling this program here, and then suddenly there are errors in this code here, which is not exactly the same as this code here. And these classes here did not exist in your initial program here. So if there are errors while compiling this here, it's going to give you errors on this code here, which is likely to be that it's not this code that the compiler refers to as errors is not code that you had in your original program. So that's why the errors are seemingly coming out of the blue as something that has nothing to do with your program. That's part of what you have to deal with when you use templates. Okay, so let's go and see some simple example here. So here what I want to do is I have a max function. Same function name, same exact kind of behavior. I want to find a maximal value between two ints, maximal value between two characters, or maximal value between two floating point numbers. Sorry, here. So then what I might want to do, if I have to do this, and I'm not aware of templates, then I say I'm going to have one function for each, okay, because this is max of two ints, max of two chars, max of two double or float. So I go implement my max operator for int, max for char, max for float. So I might say I'm going to use this, which is correct code to compute the maximal value between two values for these particular types. Okay. Now, what's of course very important and intriguing to see is that these three functions are almost exactly the same. In fact, the only difference between these three functions is that here you have int int, char char, or float float. So that's exactly the good example to understand what you want to do with templates. What you want to achieve is to avoid having to duplicate this code yourself. And you want the template processor to actually generate each of these things automatically so that you don't have to re-implement them by hand every time you want to use max of two different things. Two different max of two different things of a new type. So for example, if you would want to have max of, I don't know, string, which is going to be a problem that we'll see later, then potentially what you might want or think that you want is that it's basically going to be using exactly the same code. Sometimes it doesn't work like this. That's one of the limitations of templates or generic programming in general. So the solution in this case is to write what's called a function template. So the syntax used is you have the template keyword, and then between angle brackets, you have the keyword type name. Often you would see class, okay, but it's type name is more appropriate. Okay, I'm gonna go into the details of that here. So you might see class here. So basically what it's saying is that this template here is using a template type variable, which you name T, okay, where T is a type for this template. This is a template type variable. Then what you have as a definition of this template is the exact same code that you had before. So you see that this code here, it's essentially C++ code. However, this is not C++ code. This is template meta programming code. So here you declare this is a template. This is the variable that's used in this template. And then here you have a C++ definition for this template that is using this variable here as a type. Okay, that's what I meant here by when you declare a template, it's the language that you use is some kind of hybrid between the metaprogramming language and C++. And then if you have this main function and then you call max of these things here, and then the compiler is going to realize that there is a template for a function named max with two parameters of the same type. So then it's going to generate essentially this here when it sees that. It's going to generate this here when it sees that. And it's going to generate this here when it sees that. Okay, calling the template metaprocessor to generate these functions. Okay, These, in this case, these are free function templates. You can have free function templates. You can have operator templates. You can have class templates. You can have member function templates. In this case, it's a free function template. So let's say here we have a class template. So again, it starts with template and then type name and then the name of a variable. You will see the vast majority of examples you will see, or the code that people use. You will see this T used, the variable name uses T. That does not mean that you must use T. It's just that it's all, when people learn about templates, all you see is T as used as the template variable name. So you will see T everywhere. Doesn't mean that you must use T. So here, this is a template that uses the variable, the type variable T. Then you have a class declaration here. And then in some places when it uses a type, this case is the type of element that is stored in the stack is actually a pointer to a type T. So if you have a stack of int, then it would actually be, now I see, didn't update. Anyway, we'll see. Because I'm now wondering if I have the right slide set, but we'll see. If not, then I'll pause and load the new ones. Okay. So I have here basically a template class, or a class template. So you see that it's a stack implementation. The only difference between a regular stack implementation that you might have in regular C++ is that it uses a type variable. Okay, so that's the only difference between a class template and a regular class. There are other differences which we will uncover as we go here. So it seems that this is a regular class, but when you go into the details of how you compile it and some other things, you see that it's pretty different, especially on how it's processed and compiled, as I explained earlier. So, and here in your main function, another thing here is that I'm declaring here or defining the functions, the member functions of this class. For example, the constructor here is actually defined here. And the push function is defined here, and my pop function is defined here. So you can actually provide the implementation of your template member functions as we used to do earlier, except that in this case, they would have to be template functions. They just happen to be template member functions, right? So, and we'll see later that it's probably best to actually provide the implementation of your methods inside of the class declaration. We'll see that later. So let's assume for now that they are separate. If they are, then they need to be themselves also templates because they are using this type T here. For example, any of the member functions that is using the type that is referring to this member here, stack PTR, needs to refer to this type here. So then it also needs to use a type variable. Thus, it is also a template. Okay. You might have some member functions that don't use this type, that don't refer to stack PTR and never refer to the type of stack PTR, in which case they don't need to be templates. Exactly the same concept you have in Java, in fact. Okay, so these are, again, this is your meta language that you're using here. And then inside here, you see here in your declaration of the stack member function, you're using these angle brackets here. Of course, this is the meta language that comes in here, okay? You don't have these angle brackets in C++. This is a notation of the meta language, which needs to be removed and translated into regular C++ code before it's compiled. by the template meta processor. So inside here in my main function, I actually refer to stack of float and stack of int. So that's what is going to lead the compiler to ask the template processor to first find the definition of the stack template and then generate a class stack of float, as well as all the corresponding member functions for stack of float, if they are being used here. For example, here I'm referring to push. So that's going to basically tell the template process, have the compiler actually ask the template processor to generate a push push function that relates to stack of float. Okay. They basically are generated on demand as you are using them. If you don't call these functions, they are not generated. The template instance is not generated. So using pop and push, so they are being called here. They are being called here, so the push and pop for the stack of float is being generated and then eventually linked. Then it comes here, and then you have stack of int. So then again, it's going to call the processor, which is going to generate a class stack of int. And then it's going to generate here, when you call push, it's going to realize that it's calling this here. So it's going to generate a push function for a stack of int. And we use pop here, it's going to call the processor to generate a pop version for stack of int. And then compile it and then link it. You can also have template operators. So an operator is not very different from a function. So yes, you can have template operators, either the member operators or the free operators. You can still declare your template operators as a friend of a class, as we saw earlier. So here's an example that I designed in the past days. I did not totally design it myself. I took it as it's inspired by a website that I found. That this article is one of the best articles I've ever found explaining something about programming. I'm going to show you the reference, these two references here. It's essentially a model of clarity of explaining how to implement smart pointers using C++ templates. So if you have some time to read these, it's extremely interesting and very well done. So my example here is heavily based on these. The code that I present here on the slide, it's a simplified version of what I actually designed. If you look at the code for the resources for lab 11, you will actually find this 11. Yes, it's 11, lab 11. So you'll find this code here, but augmented with things that allows you to actually see how it's executed. But here I'm not going to explain that. So you might know smart pointers. For example, you might know auto pointer, which is now deprecated. It's interesting, but it's actually not so safe. It enables you to automatically allocate and deallocate resources, but there's pitfalls to the use of auto pointer. Okay. So nowadays you actually have what is called unique pointer or shared pointer, okay, which are more restricted, but also more safe. Not going to go into the details here. I'm just going to explain briefly this here in the lab. The lab instructor will be going over this in more detail. Okay. I strongly suggest that you take these programs and run them and see and try to trace. Basically, what I do is I output to the console a trace of what's happening, and then my code is instrumented so that it outputs something that allows you to see what is actually happening. Okay, so please go in the example and run this code and try to trace it. Essentially, what is smart pointer? it's a template class that essentially what in this class, the classes that are instances of this template class, they are simply an object that contains a pointer. Okay, extremely simple. Except that what it does is that it automatically somehow manages one of the difficulties, as of course you should have realized by now when you use pointers, is to figure out when you should actually allocate memory for the pointer and then deallocate memory later on for the pointer. Okay. That's of course one of the difficulties of your what is called a raw pointer. Raw pointer is basically a normal pointer that you use. That's opposed to a smart pointer, which is what I'm explaining here. So smart pointer object is a regular object. The smart pointer is not a pointer. It's an object that contains a pointer. Okay. Very important to understand, because if the smart pointer would be a pointer itself, then it's going to be itself a raw pointer, and then you would have the same problem. So it's a regular object that contains a pointer, and this class, the smart pointer class, helps you manage the memory allocation of that is assigned to the allocated memory that is assigned to this pointer that is inside of this object. So for example, default constructor, what it does is if this is not null, then it will actually make the object, the pointer inside of the auto pointer or the smart pointer, to point to an object that you have created externally. Okay. So and then if you want to actually use a constructor, a copy constructor, then basically what it does is it copies, it makes a deep copy of the object that is pointed to by this pointer, and then creates a new version that has a deep copy of what was pointed to by the original object. Okay. So you see that it is making the deep copy, it is implementing the deep copy, so you don't have to bother with it. Okay. Then you might also implement the assignment operator, which is implementing everything we saw related to the correct implementation of assignment operators. Okay. So for example, checking if the two pointers are pointing to the same or are the same pointer. Then if not, then you would actually delete the resource that is being pointed to by the left-hand side of the equal operator. Delete this resource so that you can assign the resource that is pointed to by the right-hand side operator, operand, and then assign it to this one after you actually made a copy of this resource that was pointed to by the right operand. So you see here, this is essentially some kind of smart pointer that implements a deep copy mechanism or semantics. We'll see later in the next slide, I'm going to have a slightly different kind of auto pointer or smart pointer. Then when this pointer object goes out of scope, then it can actually free the resource that was used by this pointer, thus disabling, in most cases, if not all, memory leaks by using this kind of pointer. Okay. So here you have the implementation of the destructor that basically releases the resource, that deletes this pointer, that deletes the, for example, memory allocated to this pointer. Then, of course, you should implement the star operator and the arrow operator that enables you to dereference this pointer. So you see here, it's actually quite simple. These are all things that we saw before, all concepts that we saw before. Copy constructor, deep copy constructor, deep copy assignment operator that implements all the required mechanism for an assignment operator, and then a destructor that deletes the resource. It's very simple, but it's very effective, and that somehow enables you to use pointers in a much easier way than if you use raw pointers, and then you have to do all of this here manually every time you use the pointer. Then here's a variation here. So it's essentially exactly the same concept. I have another class or template class here. It still contains a pointer, except that here, what I want to introduce with this example is an alternate version, which is implementing what is called move semantics. Okay. So the previous one was actually using deep copy semantics. This one will actually implement move semantics. What that means is that, let's say you have an assignment operator. So the right-hand side is assigned to the left-hand side of the operator. In the previous case, we actually had, you take the right-hand side, you make a copy of this right-hand side, and then you assign it to the left-hand side. Okay? In this case, this was in the previous case, it was a deep copy semantics. Whereas here, what we're going to have is that we're going to move the resource. In the previous case, we copied the resource and then assigned it. Here, we're going to simply move the resource. So if you have the left-hand side and right-hand side, then if you use this semantics here, you're going to take the resource on the right-hand side and you're going to move it to the object that is on the right-hand side and basically delete this one here. Okay, so that the resource is not going to be copied. That's actually the main advantage of this here, is that if you implement that, in many cases, in fact, instead of making a copy of objects when, for example, the parameters are passed to a function or a value is returned for a function, it's not going to make a copy of object. It's rather going to move the resource to the reference that you are using, the value that you are passing, for example, to a function. Okay, so implementing this move constructor, or this move, this smart pointer that uses move semantics, it results in consuming less memory. Okay, it is more restrictive though. This here, okay, this code here cannot be used in all cases, but in cases where it can be used, it actually reduces the number of objects that are created when you use smart pointers of this kind. Okay. For example, when you pass an object by value, it refrains from actually making a copy. It rather moves the things, the object as you pass them, or pass by reference, I'm sorry. Okay, so one of the things that it uses, which is not something that you see often, is this notion of R value reference. So we saw earlier the ampersand operator, which is basically used to create, or for example, declare a reference variable, or for example, declare a reference parameter. Okay, so this is a general reference. Okay. And the general reference is something that has been there since the beginning in the C language. But later on, as people were designing C++, they found that this was rather restrictive. They actually designed this new notion that appeared in C++ 11 of the notion of an R value reference. So what is the difference between L value reference and R value reference? Essentially, that it's not something I mentioned a lot in the course. It's an essential notion if you want to understand deeply how things work in C++. So essentially, an L value is, you can think of it as what is it on the left of an assignment operator and what is it on the right of an assignment operator. So what is on the left of an assignment operator is an object that you can assign a value to. Okay. Normally, this is an object that has a name, because there are some objects that don't have a name. If you call new object, and this object does not have a name, it starts having a name only when you assign this new object to an object that has a name. Okay. So this object that you have, that you create using new, is actually an R value. Okay. So, and then the L values, well, is generally an object that has a name. It's more complicated than that, but that's what is the basic notion of it. Now, the general notion of a reference is an L value reference, basically a reference to something that has a name. Now, if you want to create, if there's some cases where you want to create references that only apply to R values, then you can use the notion of R value reference, which is using double ampersand. You see that's what I'm using here and the definition of my constructor, as well as my assignment operator. So essentially here what it says is that I can only call my move constructor on objects that are an R value. If the object is not an R value, you don't have a, you cannot use this move constructor. Okay. In this particular version here on the slide here, I actually, in fact, deleted the regular copy constructor that uses the L value reference here. So here that basically if you have these two things here, where you disable the L value reference parameter to your copy constructor, and basically that means this class does only work when you use the copy constructor by passing an R value to the actual parameter of the copy constructor. And then you see that what this constructor is doing is essentially moving the resource from the left-hand side to the right-hand side of it's actually taking the resource of the object that is passed to make a copy. It's removing the resource from this object and is putting it inside of the newly created object. Okay. So this way, there's always only one there's only one resource that is implicated in this transaction here. Okay. Then for the assignment operator, same thing is happening here. So I have my assignment operator. It takes a parameter which is a R value reference, and here I disable my regular L value reference parameter equal operator. That means that if I'm using this implementation here, exact implementation, then I have two objects of this kind. I go A is equal to B, then this B here must actually be a R value, or else it's not going to work, because if it would be an L value, then it would only be possible if I have an implementation for this one. If you look in the code that I have in the example, I have actually enabled both of them. Okay, but here for the simplicity of the example, I've disabled it. So in this particular example, this is a purely restricted a smart pointer that is using only move semantics. Okay. So you see that it does all the things that we had before. It deletes the resource, it have constructors and so on. The constructors are doing the move. For example, the copy constructor is moving the resource from the parameter object to the newly created object. The assignment operator is actually moving the resource from the right hand side operand to the actual left hand side operand, which is the object that's being assigned to. So you see that this is a new concept I'm introducing here, the notion of R value reference and the notion of move semantics. You don't have to use move semantics, but in the cases where it can be used, it can actually significantly reduce the number of objects that are being created at runtime. Okay, that's the main advantage of using move semantics. It does not work for all designs that you may have, though. In some cases, you actually need to have the left-hand side and the right-hand side to live after the operation has applied, in which case you would not use move semantics. But if you can use move semantics in your design, it leads to less number of objects being created as the program runs. Okay, so close parenthesis on smart pointers. Smart pointers is a very good example of use of templates. So you see that it's not, templates has a tendency to create things which are simple, but of very broad application. Okay. Of course, you could have a smart pointer that points to anything. It's applicable to any type. That's what is the power of templates. Enables you to describe a mechanism that applies to things of any type. Okay. This mechanism is generally a not so complicated mechanism, because as we will see later, what's happening if you want to generalize it to all the types and your mechanism is very complicated, the more complicated is your mechanism, the more likely it is that it does not apply to certain types in particular. Okay, so that's what we're going to see right now. That's why templates very often end up being, the code that you see inside the template definitions is very unlikely to be very complicated code. So the limitation of templates is that, yes, they aim to apply across all the different types, but then there's very often limitations in how you manipulate objects of different types. So here's a good example here. So let's say I go back to my max function. So here the max function was used on ints or chars or floating point numbers. Here I want to use it using strings or a char pointer to a character. Okay. Now remember that my code for the template was basically this code here. If A is greater than B, then A, else B. Essentially, that's what this code says here. Now, if you actually execute, if you compile this with this template definition, what's in fact going to do is that this here is going to be interpreted as a pointer to characters. Now, if you apply A greater than B on pointers to characters, then it's going to determine if the pointer value is greater than the other pointer value, which is irrelevant because here you're just basically comparing memory addresses. You're not comparing the strings themselves. Okay. So essentially, it means is that this code here that I have does not apply to this here. It does not apply to strings or pointers to characters. So that's exactly what I was mentioning here. So here the person probably hoped that this would work for any type. It does not apply to any type. Okay. That's the great limitation of templates. That's why you would see very often templates code is very simple. The more you add more code, the more it's likely that the code you have does not apply to certain types. Now, what do you do in this case? There's a solution to this. So what you can do is to have an explicit template specialization. Basically, what you would say is, there's instances when you have this template here. This template leads to have several instances. For example, one of the instances max of int, or max of char, or max of float. Then what you can do is to readily, right away, specify here's the max function, for example, in this case, for char star. So here you're declaring a template that does not use a variable, and this is a template for max of char char. Okay. So you're essentially writing your template instance hard-coded, and you declare this is a template. Then when the template processor is going to look for a template of max char star, then it's going to see this definition and it's going to use it right away without generating it. Okay. So, and then the more you find other types for which your generic definition of the template does not work, the more you would need to have explicit template specialization, which is of course defeating kind of the purpose of templates. If you define a template and then you need to have a lot of explicit template specialization, it's not a very useful template. So yes, you can do that, but it's not an exemplary usage of templates. In Java, you can actually have restrictions on your type parameters that enables you to use a certain generic class for a specific kind of types. You don't have that in C++. Okay. Okay. So here's another example of explicit template specialization. So for example, here I have a template named formatter, and then it has a pointer to this type here. And then the point here is I'm printing. Essentially, I'm printing the value pointed to by the pointer. Now, if I want this to apply for a char star, again, that's the counter example, then I would need to have star star empty and not star empty, because if I print star empty, it's going to print the pointer value of this pointer. So you see that using pointers is often creating some problems in your templates and requiring that you have template specializations. Okay, so here we go into some of the pitfalls. Or you might say that this was a pitfall also. I would kind of agree. You know, if you're designing a template and the code in your template does not apply to some types, then you have to use explicit template specialization. There are other pitfalls, unfortunately, in the usage of C++ templates. I'm not claiming I'm pointing you to all of these pitfalls, but I'm just discussing some of them here. Okay, so let's say one of the things is, let's say you have in your template class a static variable. Now, the notion of a static variable in a class is that this variable is a variable that is common to all objects of that class. Okay. Now, if you have a static variable in a template class, then what's going to happen is that the template processor, for example, this is a stack. This is a stack template, and then you use a stack of int. And then there is a static variable inside of your stack template. Then you use it as a stack of int. Then the template generator generates a class stack of int. Then later on, if you use a stack of strings, then it's going to generate a class for a stack of strings. These are going to be two different classes, stack of int, stack of strings. And both of them are going to have this static variable, but they're going to be independent, because this is a stack variable for the class stack of int. This is your static variable for a stack of string. So if you have static variables inside of a template class declaration, you have to be aware that you're not declaring a static variable that is essentially global to all the possible usages of your template. It's going to be local to the objects that are, for example, stack of int or stack of string. If you want to actually initialize the value of your static variables, you would have to use this notation here, which is essentially using the template declaration here. So essentially it's declaring that this variable S here belongs to the type X, which is this type here, or X of int in this case. Okay, so you see here that you're declaring the initial value of S for the class X of int. You also, if you would use a X of char star, then you would have to declare the initial value for S of for the S variable of X of char star. And you would need to precede that with template to signify to the template processor that it has to process this line. Okay. So if you use static variables in a template declaration, the static variable is local to each of the classes that is being generated by the template processor. Here we go with one of the greatest pitfalls or limitations, or call it as you want, of using templates. It has to do with how do you declare the member functions, or define rather the member functions of your template class. Okay. First of all, template declaration or definition. Simply you have a template class definition. This is not a class declaration. This is a template class declaration or class template declaration. If you have a template function, this is not a function. This is just a definition for the template processor to use that will generate functions and classes. As soon as you have something that starts with template, you cannot say this is a class. It only becomes a class after it's been processed by the template metaprocessor. As I explained much earlier in this lecture here. So the thing is that because of that, then you need to have, because what is actually compiled by the compiler is code that is being generated. And that means that as this code becomes compiled, then it actually needs to contain the definitions for these templates, especially functions that are referred to inside of the corresponding template class. So let's go into with an example. So let's say we have a stack template class. Okay. Then if that would be a regular class, and what we saw is that if you have a regular class, then you should have in the .h file, you have the class declaration. Then in the .cpp file, then you have the implementation of all the member functions that are declared in this class declaration. And then in the stack.cpp file, you would have #include stack.h. Right? That's how we saw that you should organize your code. Okay? And then eventually you could have a stack driver, other compilation unit that may use stack of float or stack of int. And then it would actually trigger the execution of these classes, of these classes and their corresponding functions at compile time. Okay, dog's dog barking. Sorry about that. Okay, so so I have my stack driver that is using a stack of float and a stack of int. As the template, the compiler sees these calls here, or these declarations of stack of float and stack of int, then it would actually need to have the declaration for this template class. Okay. So in this case, in this code here, this is preceded by #include stack.h. So before the compiler comes here, it already read beforehand this file here. So it started by reading this here. Now the compiler is aware that there's a template named stack. Then when it comes here, it sees stack of float. Then it calls its friend, this template meta processor, please generate me a class stack of float. Then it goes and gets the template meta processor, gets this template declaration, and then generates a class stack of float. Then compiler can continue. And then when it comes here, it says you call a push function. So push was not actually defined here. Okay. So then if push, the definition of push is not here, then the compiler is going to assume that it's going to be somewhere else, which is going to be resolved by the linker. Okay. And that's the problem here. Because as I'm actually processing this here, I never actually, the compiler never actually reads this code here. So as I'm calling push here on my stack of float, eventually what the linker will want to see is a push function that applies to stack of float. But this actually never got if the stack of float is the template definition is not accessible here, then the compiler cannot generate this function here, which is going to eventually lead to a linkage error. Okay, and that's one of the things that is doubly confusing, is that this compilation is going to go, it's going to say everything is fine, but then it's going to basically be the linker that is going to say there's no such thing as push being defined. Okay, because the compiler basically left it to the linker to resolve this the call to an external push function that was defined and generated code for in another compilation unit. Now, if this was never compiled anywhere else, then the linker would say there's no such thing as push of stack of float, and there's no such thing as pop of stack of float, and there's no such thing as any of these things here. Okay. So the problem here is that the definition for this template member functions was not accessible in this compilation unit. The solution is for these things here, these definitions here, to be inside, to be accessible inside of this compilation unit. Now, there's different solutions to this here. So you might say, okay, I'm going to take these method definitions and I'm going to put them in my .h file here. That's not very elegant, as you don't see that you don't see that anywhere. Of course, the much better solution is to say, anytime you have a member function definition in a template, you provide the definition inside of the class itself. Okay, that's what you will see most often. So in this case, the definition of the functions would be defined inside of the template itself. Thus, they would be accessible right away here. Okay. So that's an additional problem that you have to deal with when you when you define your own templates. You should not ever define your template class in a .h file and then have your methods defined in a .cpp file. They should all be in the same .h file as inline functions, essentially. Okay, so that's what is the problem. So as I mentioned here, so you have different solutions to this. Declare all the methods as inline. That's the best solution. Or put all the methods definition in the header file. That will work, but that would be confusing or not so elegant. There are other things that would work, but would be not advisable. So you might say, okay, so here, if I have this design here, .h file, class declaration, .cpp file, method declarations. Okay? We already saw that this doesn't work if you do it this way. Now, if you want this code to be accessible inside of this compilation unit, then you might say, oh, I'm gonna hash include stack.cpp here. So yes, this is gonna work, okay? But of course, we saw earlier on that you should, as soon as you say, as soon as you read in somebody's code hash include file name.cpp, you can safely say that person is not very good at C++. Okay. You should never have hash include file name.cpp. It would work, but that would be contrary to what everybody agrees is good coding practice. So that's basically the solution here. Another solution would be that in your, what's not working here is that from the when you compile this here as a separate compilation unit, in this compilation unit, there's actually no use of these template member functions. The template member functions are sent to the template metaprocessor when these functions are used. Just like here, if this template is here, and then I remove these variables here, then this template is not used and these classes are not generated by the template metaprocessor. So the problem here is that when the compiler compiles this here, there's no use inside of this compilation unit. There's no use of stack or push or pop. The use is made in this other compilation unit here. So if you want to force the compiler when it compiles this here, to actually generate instances of these member functions, then what you can do is to put template instantiation declarations inside of the file. For example, saying template class stack of int, template class stack of float, for example, at the end of this file here, in order to force, as this is being compiled, that would force the compiler to generate a class stack of int and stack of float as it's compiling this, and thus generating the stack of int and stack of float in this compilation unit, which would then be available to be linked with this other compilation unit. Okay. So you see that if you don't really understand this notion of compilation unit and then the linkage and so on, it becomes very difficult to actually understand how to properly use templates. Okay. Templates usage is one of those very good examples of why is it that in C++ you need to know all the details of how it works in order to actually use it. You could use Java generic classes without knowing exactly how it works. Okay. But very different from C++ templates. So that's it for that. That's one of the great problems that people see with defining class templates. If you declare a class template, best thing is to actually declare inside of the class or define inside of the class every of the member functions of this template class. So here, I'm going to very briefly go over that here because it's not really material for this course. I just wanted to show what's the difference between C++ templates and Java generics. So you've learned how to use Java generics before. You might think that it's the same as C++ templates. You would be totally wrong. Okay, it looks like the same, but of course, when you start using it, you realize that it's C++ templates are much more difficult to use. They give you weird errors, more errors, and so on, because of all the problems that we saw before. okay, which relates to how they are actually processed. A Java generic class is almost like any other class. That's one of the things I'm going to explain here. I'm going to briefly go over this, okay, because this is not really material for the course. But there's this misconception, among students especially, saying that Java generics and C++ templates is the same. It's not the same. Okay? Same concept, but in terms of how you use it and how it works, it's not the same at all. So how does it work in Java? In Java, you have a generic class. It still uses the angle brackets. It still uses the type variable and so on in the definitions of your classes or your free functions or of your member functions and so on. Okay, so looks like the same. So you may think, well, it's the same. So what happens when you do when you declare an abstract or a generic class in Java? Java actually use what is called type erasure at compile time. There's no such thing as the template metaprocessor and so on. It's basically an additional step in the compilation process, which is called type erasure. So essentially what it does is it takes what is inside of, I'm being very succinct here, and I'm skipping some of the details, of course. So type erasure, what it does is that it basically removes these angle brackets and these types variables. Okay. So if you, for example, declare a box of int, then it would remove this here and then replace t by int everywhere. Okay. So essentially, that's what it does. Again, very simplified explanation. Okay, and then this class box actually becomes a regular class. It's not exactly a regular class. It's called what is called it is what is called a raw type. You can still use it as a normal type, but there's special considerations to it. So this class box is basically the same class on which type erasure is being applied, depending on where you use it and how you use it. So you see that it's actually very different. There's no such thing as a box of int and a box of string and a box of this and a box of that at runtime. It's just that the type erasure is applied every time that it's actually used to a certain to a certain purpose. This has to do also with this you see, this is basically restricting the box class to the type number. So you can only have a box of something which is number or a subclass of number. So the type erasure, what it does is basically replaces t with the number, which would make this actually works for anything that is either a number or a subclass of number. So that's what the type erasure is doing. So that there's a double use to actually this restriction that you have on the type parameter. Okay, it enables you to be only able to use this generic class for a certain subset of types, and also it has a role to do with the type erasure procedure. So that's how Java actually processes generic classes. You see that it has very little to do except in concept with the notion of template programming and a template processor that generates classes and so on, and basically is a code generator. There's no such thing as code generation or template processor in Java. So as I usually do, here comes some kind of analysis that we can get from what we saw. So what is the impact of using templates? So that's using templates makes your code slower? Does it make your compilation run slower? So it does not per se actually make your execution go slower, because as we saw, it actually executes regular classes that are generated by the template metaprocessor. So it does not result in code that runs slower. However, this template metaprocessor has to be called at compilation time. So the more you use templates in your code, the more it actually makes the compilation of this code slower. It takes more time to compile code that uses templates rather than if it does not use templates. That's acceptable because that's not at runtime. Okay, it may result in unnecessary code bloat if explicit template instantiation is overused. So if you provide your explicit definitions for so many different types, then this code needs to be incorporated in the code, basically the code base that is being translated into an executable. Okay. The more you have this explicit template instantiation, the more you have code that is being generated. If you don't call them ever, then they're still going to be there. Note that there is, of course, some compilers that will optimize that and actually remove them, but it may result in code bloat. In terms of design, as we saw before, the notion of having your .h file and your .cpp file. If you're using templates, if you're defining a template, basically what it says is that forget about the CPP file. A template class should include always its own method definitions as inline functions because of the way that the template class is actually processed at compile time. Okay, so this is kind of a blot into this notion that you should have .h, .cpp file. If you have templates, then you only have .h file. Of course, as I mentioned earlier, many times at this point, when you use code when you develop code that uses templates, if there is some errors that result or either compilation error or linkage error, these compilation errors are likely to be as a result of compiling code that was generated by the template metaprocessor. So of course, then your compilation error or linkage error are likely to be very cryptic because they are the result of compiling generated code. So you may read these errors and you say, oh, I never define a class blah. It's basically a class that is generated by the template metaprocessor that is referred to in the error in the error that is given to you by the compiler or the linker. Makes it very difficult to actually figure out what's the meaning or source of the errors. So many different interesting here references that I gave, either historical or this one here, which again, I repeat, was excellent, 2 articles. Thank you for passing by.